Hello everyone, this is Amit Bhardwaj and I am Senior Chemistry Lecturer in Sri Chaitanya Gosala campus. With our new program, we are trying to brief some chapters in short time using questions definitely, and we will point out some points which will help you to solve your questions for the upcoming NEET exam, right? So we are starting with our chapter Haloalkanes and Haloarenes, right? So we will revise it through questions, right? So as you can see, the first question is depending on the classification of haloalkanes or aryl halides, we can say. Whenever you see halogen is present on the double bonded carbon, we call it vinylic halide, right? And if this double bonded carbon is benzene, so we call it aryl halide, right? And if halogen is present on the carbon which is next to what? Double bond. So we call these as allylic halides, right? And if we have benzene ring and on the next carbon we are having halogen, we call this as benzylic halide, right? Instead of this, we have some more points as well in classification. Like you can say, if on same carbon we have halogen, we call this geminal dihalide. Similarly, if we have halogens on the adjacent carbons, we call these vicinal dihalide, right? So using this, we have to opt our best answer here, okay? So you can see the options. It is our allylic halide, so this A should give us what? S. This is our vinylic halide as X is present on double bond carbon. Here both chlorines are present on same carbon, so it is geminal dihalide, and here chlorines are present on adjacent carbon, so that's why we will say this is our vicinal or weak dihalide, right? Next question is related to the preparation of haloalkanes using alcohols basically. It is one of the first question in NCERT, you see the first topic. So first of all, in short, if I say I have alcohol, so from alcohol I want to make haloalkane. So we can use HX like HCl, HBr, HI. Otherwise you can use PCl3 or PX3, which will give us RCl, right? And with this it will give us S3PO3. Or you can use PCl5. PCl5 will give you RCl, POCl3 and HCl, right? And one of the best one, if you use thionyl chloride, SOCl2. So it will make RCl and produce here SO2 and HCl. Both of these are what? Both of these are gaseous. So it is very easy to separate these from our main product. So let us see the question. The best method for the conversion of alcohol into alkyl chloride, they are asking, right? So best method is definitely using what? SOCl2. Actually, if we use SOCl2 alone, thionyl chloride alone, we call this Darjan's method, and yes, it is the best method. And the mechanism for that will be SNI. I'm saying once again, with SOCl2 if you use, it is SNI mechanism which will give us the retention in configuration. And if we use SOCl2 with pyridine, in presence of pyridine, the mechanism become SN2, in which we will get inversion. So definitely this is the best method because the byproduct formed will be gases and you can separate them from our main product very easily, right? The next thing is again depending on the preparation. So they are saying ethylene dichloride we want to make, right? It means we are having CS2, ethylene dichloride. This is our ethylene dichloride. So how we can make it? If you see carefully, we are having ethylene glycol. That means here we have CS2 and it's OH, right? So these OH can be replaced, right? We can take here as they are mentioning this. If we take ethylene glycol, so we can put here HCl, it will replace the OH by Cl, right? Clear? So yes, ethylene dichloride can be prepared by adding HCl in ethylene glycol, right? Next one if we come, so again it is from the preparation of haloalkanes and based on some name reactions, right? First of all, as B and C both are given same, so I will rectify this little bit. This B is what? I am having here diazonium salt, and in diazonium salt I will add CuCl with HCl, right? This will give us chlorobenzene, right? So instead of this, we have this one, right? Now we have to see the options. First of all, we are having alkane. In alkane, you are adding here Cl2 in sunlight or Cl2 in heat you can take. It is free radical substitution from our alkane chapter, right? So the Cl will replace hydrogen from here. I will say the Cl radical will replace H radical from here. So we can call it what? Free radical substitution. So this will go for the free radical substitution, right? From alkane chapter, very important. Now, this reaction is known as Sandmeyer reaction. We are converting diazonium salt into chlorobenzene, right? So yes, with this reaction, means this one reaction, will go for Sandmeyer, right? Now, we are having Finkelstein reaction, in which we are replacing our Cl by iodine. Remember one thing, to prepare chloroalkanes or bromoalkanes, it is easy. But to prepare iodoalkanes and fluoroalkanes, it is a little tough. That's why we use halogen exchange reactions. So Finkelstein and Schwartz both are halogen exchange reactions in which we replace other halogen by iodine if I am talking about the Finkelstein reaction, and if I replace halogen or bromine here like by fluorine, this is known as Schwartz reaction. So for third option we will go for Finkelstein, and for the D we will go for Schwartz reaction, right? Clear? So please remember these two, or I will say three named reaction, very important, right? Yes, from here we can opt our answer also, like A is giving us which one? Q, okay? A is giving Q and B is giving us S. So we can opt A is Q, B is S, right? Only one option these two are having, and remaining you can see. The next section is aryl halides cannot be prepared using PCl3, PCl5, or you can say SOCl2. Just now we have used PCl3, PCl5, SOCl2 to make haloalkanes, right? Because ROH, if we see, if we add these reagents in alcohol, that is ROH. So here you will not find any partial double bond character. So if I take example of SOCl2, easily we can replace this OH by Cl, fine. But if you take the same things in case of phenol, here this phenol, this O and this carbon will have partial double bond nature. Why? Because you will see O have lone pairs and here we have pi sigma lone pair. That's why conjugation will take place and partial double bond character will come in this bond, right? And we can even call it plus M effect of OH, right? This lone pair comes here, this will move here. So partial double bond character here in carbon oxygen bond make it tough to break this bond. So you can't replace it very easily, right? That's why you will say they're asking aryl halides cannot be prepared from phenol using these reagents. Definitely it is having carbon oxygen double bond, or I say partial double bond character is there. That's why it's tough to replace it, right? Next, if we come in the preparation of chlorobenzene from aniline, the suitable reagent, right? They're saying chlorobenzene from aniline, very important. We are having aniline. All the aryl halides can be prepared from diazonium salt. Very important point again. If we do its diazotization, we can use here NaNO2 with HCl, or directly we can say what? Directly we can say we are having HNO2. So it will convert it into diazonium salt. This is very important compound to prepare benzene compounds basically. And in this, if we can add CuCl HCl, right, it will give us chlorobenzene. This reaction just now we have seen, it is our Sandman reaction. You can use Getterman reaction as well. Okay, so we can see now. Yes, what is it? Nitrous acid followed by heating with Cu2Cl2 you can say, or you can say CuCl with HCl. Both are same thing. So it is Sandman reaction. Just now we have seen, right? Next thing is just same. Instead of chlorobenzene, they are saying to make fluorobenzene, right? We want to synthesize fluorobenzene. As I said just now, if we have aniline, in aniline, if we do its diazotization, we will see we get N2 positive, Cl negative here. And to prepare fluorobenzene, we have some special named reaction that is known as Bose-Schiemann reaction. So in that you will see, we will take HBF4 and we will heat this, right? So it will give us fluorobenzene. So yes, you can see here we are having D option from aniline by diazotization followed by what? Heating diazonium salt with HBF4. Okay, it will give us fluorobenzene. If I write the name of this reaction, it is Bose-Schiemann reaction. It is also a named reaction, right? Clear? That's why very important. Now, the next question is depending on the physical properties, right? And they're asking about the highest melting point, right? So, melting point basically depend on the symmetry. More the symmetry, more the packing, better packing, more the better packing you can say, higher the melting point. So you have to find symmetrical thing here, and especially in case of dichloro or dihalobenzene, if I talk about, so you can see the para-dichloro. This is very symmetrical. Because of symmetry, the packing will be good, and that's why the melting point will be high. If I compare the melting point of dichlorobenzenes, so you will see meta-dichlorobenzene has the lowest melting point, then ortho, and then para. Just from NCERT, right? It is important, they can ask. I will add one more point. The boiling point depend on the intermolecular forces mainly. Boiling point depend on the intermolecular forces. So, more the dipole moment will have more chances to have intermolecular forces. So, you will see the boiling point sequence will not be same. In that case, ortho will have higher boiling point because of higher dipole moment. So, more interactions will be there and higher boiling point will come. Next question is depending on the SN1. Okay, we have seen some questions on the preparation basis basically. Now, the nucleophilic substitution, which is the most important topic of this chapter. Nucleophilic substitution. So, SN1, here we are trying to replace one nucleophile by some other new nucleophile. And SN1, the one word here is showing that its molecularity is 1. Its molecularity is 1, as well as order also 1, definitely. And the most important point, in SN1 mechanism, carbocation will form. So, carbocation stability, that is the intermediate, it will decide which compound will be more reactive or less reactive. So, carbocation, higher the carbocation stability, higher the reactivity for SN1, right? And even this carbocation can rearrange as well. So, if I add some points here, first of all, molecularity order 1. Carbocation will form, it can rearrange. The reactivity order, if I say, is what? Tertiary, halide, then secondary, then primary, based on the carbocation formation, right? Racemization will take place because attack of nucleophile can take place from back side as well as front side. So, you will see partial racemization, more inversion, little bit less retention, right? But partial racemization you can say. So, in this we have to see which will give us the most stable carbocation, right? If we see here, we are having here benzene. Benzene, one more benzene here. and here we have CH3. So after removing this bromine, you will see we will get this carbocation. 3 alpha hydrogens, lot of conjugation from 2 benzene rings. Here I am having 1 benzene ring, 2 benzene ring, but 3 alpha hydrogens are missing here, less stable carbocation. Here we have only 1 benzene ring, so less stable carbocation again. And here definitely it is allylic having conjugation, but only conjugation from 1 benzene ring, and alpha hydrogens are also missing here. So that's why it is the most stable carbocation, which make it most reactive for SN1 reaction, right? The next one is, as I expected, they are asking about SN2. SN2 is also mechanism for substitution. Why we call it SN2? When this nucleophilic substitution will be bimolecular, or I will say the molecularity is 2. No carbocation formation, right? So attack can take place from the backside only, so it will give us only inverted product, or inversion can take place if we have chiral carbon, right? So now the reactivity order is primary halide, then secondary halide, then tertiary halide, because of the steric hindrance factor, steric crowding. The outgoing nucleophile will go and the incoming nucleophile will come at the same time. That's why you will see the crowding will take place. Already there are 3 things. One nucleophile is going, one is coming. So crowding factor is more important here. Steric hindrance you can say. So if you can see, if you have haloalkane with lesser crowding, it will be very reactive. That's why the order is primary, secondary and tertiary. Fine. Now the next thing is the leaving group. Rx will leave from here, right? That this bond will break, na? This bond will break, right? So better the leaving group, easier the reaction. If this will leave easily, then the new nucleophile can come. So on that basis, if you see the Ri bond, they are asking the order of reactivity, right? So we can come here, right? Because the Ri bond is little lengthy and easy to break, whereas RF bond is small and tough to break. So on that basis, they are giving this order. On the basis of leaving group, alkyl halide are same. So on basis of leaving group, better the leaving group, better the reactivity. And even this order will remain same for SN1 as well as SN2. There is no difference in that, right? SN1, SN2 order can change when you will have different alkyl groups. For halides, like you are changing the halide, the nature will remain, or the order will remain same. So it is based on leaving group nature. Now they are asking which of the following is optically active compound, right? Students face problem in these questions definitely connected to optical isomerism or optical activity. The best method to check out of the following 4 options, which option is optically active. So you have to choose option with 1 chiral carbon. A compound with only 1 chiral carbon will always be active. A compound with 2 chiral carbon, 0 chiral carbon, 3 chiral carbon, 4 chiral carbon can be active or inactive depending on it is the compound is chiral or not. But a compound with only 1 chiral carbon will always be optically active, right? So this trick you have to use. You have to find the option in which you have only 1 chiral carbon. That will be always be active, right? So, okay, I am drawing this butanol, 1 butanol they are saying. So here I am putting OH. Definitely none of the carbon is chiral here. Remember, presence of chiral carbon is not the condition for optical activity. But this trick you can use to solve the questions of optical activity. Okay. But if you see here, we are having 2 chlorobutane. So this carbon is chiral. Why? Because this contains ethyl, methyl, hydrogen, chlorine. So we have 4 different groups on this carbon. That's why it is what? Chiral. And compound with 1 chiral carbon is always optically active. So right? So we will choose this one. Clear? If there are 2 chiral carbons, 3 chiral carbons, then we have to check is it having plane of symmetry or no. But here there is no need to check, right? Next one, as we discussed just few minutes back, they are asking the reactivity for SN2. I told you just now, you can see the order was primary, secondary, tertiary because of steric hindrance factor. Minimum the hindrance, more the reactivity, right? So we can see methyl halide have the minimum hindrance. Only 3 hydrogen are present, minimum hindrance. So yes, highly reactive. Even if I want to give order here, most reactive, then primary, then secondary, then tertiary, right? Which among the following will have the meso isomer as well? Meso. So definitely you have heard these things. Meso compounds. Right? Understand what is meso compounds. Meso compounds are the compounds which are optically inactive, but they are inactive because of the internal compensation. So two conditions you can remember. Meso compound will have at least 2 chiral carbons. At least 2 chiral carbons. Without chiral carbon, a compound can't be meso. So at least 2 chiral carbon. And second condition you will see, it will have plane of symmetry. It will have plane of symmetry. And definitely meso compound will have some isomer which will be optically active, right? So we can see which one of these can follow these conditions, right? So if you look at this carefully, 2,3-dichlorobutane. If I make this 2,3-dichlorobutane, right? So you see, this compound have plane of symmetry, but definitely by actually some time we cannot see directly plane of symmetry, right? Because you can draw a compound in so many ways. Every compound, like in every projection or every representation, you cannot directly find the plane of symmetry. So what is the trick here? First of all, check upper chiral carbon and lower chiral carbon are having same groups, like upper have methyl chlorine hydrogen, lower have methyl hydrogen chlorine, and then check the configuration, RS configuration. If both chiral carbon have same groups and one of these is R and other is what? S. So yes, it is meso. They are cancelling the optical rotation of each other and net optical rotation will be 0. That's why you can say yes, it is meso, right? You will have definitely symmetry if you are searching for meso compound, right? Next thing is an alkali halide react with the metallic sodium in dry ether, reaction known as, very important reaction. In alkane chapter also we have seen. So we have here Rx, we are having sodium here, Rx again. Whenever we have metal, to avoid reaction with water, we use dry ether. Okay. So whenever you see in the reaction, dry ether is given. That's why, because they are trying to avoid the contact of water or moisture with our metal. So here, this will replace this Na will take X. So R will combine. It will make 2NX. This is Wood's reaction. Very important reaction. Wood's reaction. 1 or 2 points about Wood's reaction. You cannot prepare methane by this reaction, and we do not use this reaction to make alkanes with odd number of carbon atoms. If you use here different halides, like if I am using R, I am using here R dash, not good for the reaction, because in this case you will get the mixture of products, mixture of alkanes, and it will be very tough to separate them from each other. You can't prepare methane. You cannot use it to make alkane with odd number of carbons. Only alkanes with even number of carbons, right? And we should not use here tertiary halides, right? Otherwise, sometime elimination chances also increase, right? The next one is 2-bromopentane is heated with potassium ethoxide. So this question is related to the elimination reactions, right? If I have 2-bromopentane, right? So this carbon is having how many hydrogen? This carbon is having 2 hydrogen and this carbon having 3 hydrogens. Alcoholic KOH is given, so definitely there is chances of E2 mechanism. E2 mechanism. And mainly E2 or even basically follow Sergev rule. Hoffman rule will be followed in very few cases, like in bulky base case or very poor living group, or in even CB mechanism we can say. So here nothing is present, no bulky base, no poor living group. So simply follow Sergev rule. Sergev rule say remove the hydrogen from carbon with less hydrogen atoms. It is having 2, it is having 3. So I will remove from here, I will remove bromine from here, definitely we will pent-2ene, right? And yes, the trans form is more stable, so trans pent-2ene will form, right? As your major product they are asking, right? Next one is chlorobenzene react with magnesium in dry ether to give compound A. Further react with ethanol to yield what? Okay, this question, this type of question they asked in the last year NEET exam, right? They are having chlorobenzene. I will say chlorobenzene this way. The phenyl ring, chlorobenzene and magnesium in dry ether. Again, why dry ether? Because here we have metal. So this will make our Grignard reagent here, right? Now the best reaction for Grignard reagent is what? We can call these acid base reactions. Grignard reagent, this R negative or pH negative, always search acidic hydrogen from water, from acid, from H2S, from alcohol, wherever it can get acidic hydrogen, right? So here they are saying reacting with what? Ethanol. So ethanol to have acidic hydrogen here, right? This pH negative will take H from here and will make benzene. A very important reaction of Grignard reagent, right? So we'll get what here? Benzene. Next thing we will see the correct order of reactivity for ARSN. So first of all here, very important point is for the nucleophilic substitution reactions, if I compare, haloalkanes are more reactive or aryl halides are more reactive. So remember, haloalkanes or alkyl halides are very much reactive than aryl halides, because there are many reasons. Partial double bond is the best reason here. Because of conjugation, partial double bond will come, and that's why it is tough to break. So you can't replace halogen from here. It is not easy. Otherwise, other reasons are like pi electron cloud of benzene will repel the incoming nucleophile. That is also one of the reason. sp2 hybridization of carbon having halogen, right? So because of some reasons, you will see this is very reactive. To make these aryl halides reactive, we put electron withdrawing groups at ortho and para positions. Presence of electron withdrawing group at ortho para positions in aryl halides will make them little reactive for the nucleophilic substitution reaction, right? The more the withdrawing groups at ortho para positions, more the reactivity. Clear? So here we can see, here we are having NO2, right? 2 NO2 at ortho para, one only. But see, it is what? Meta. It is what? Para. It is ortho. So definitely, meta nitro will not help so much in reactivity. So here, most reactive. Out of these, if you see, this will help little more. This will help little more because when nucleophile attack here, the negative charge will form. The mesenhymer complex will form, right? And that carboanion, the mesenhymer complex will be stabilized by the NO2. Little bit more stable carbanion will form here instead of this one, right? So reactivity must be most reactive, then this one, then this one, then this one. And the least reactive simply aryl halide without any withdrawing group, okay? So if you want to find the option which is most reactive, first one, then go for fourth one, right? This is the answer. 1, 4, 2, 3, right? Very important question. Next thing is alkyl halide formation of Grignard reagent and heating with water yield propane. Just now we have seen the reaction of Grignard reagent. Now we have to go reverse way. They are saying we are making what? Propane. Okay, we will make propane here. Fine. From what we are making? They are saying with water they heated, right? I am taking water here. Water have acidic hydrogen. From Grignard, if you are making the propane, definitely here you will have, if I say C3, right? H7 negative. This is our R negative, and here we have MgBr. Because this will take H from here and will make propane, right? And from where we can make this definitely, if I am using here magnesium, so here I should have a 3 carbon, or I will say propane chloride or propane bromide. From this I will make Grignard reagent. This Grignard reagent will take hydrogen from water and will make propane, okay? Bromide or chloride you can say here, whatever they have given, right? Clear? Very important reaction once again. Next thing is You will see this is the benzine mechanism. Benzine mechanism, not given in NCERT, but yes, important because once they asked in the NEET exam. So first, if you take here NS2 negative and heat we are doing, overall, so you will see it is substitution. Overall, so it is substitution, but how it happens? First, you will see elimination will take place, benzine will form, and then again addition. So it is substitution, but how? Elimination followed by addition, right? So this will replace hydrogen from here, and then this Cl will go, and we will make what here? Benzine, right? Benzine is important intermediate. They can ask 1-2 question from here. Benzine, every carbon is sp2 hybridized. First point. The pi bond formed here is formed by hybridized orbitals, not by pure orbitals. This pi bond, it's a very rare thing because every time pi bonds are formed by only pure orbitals. But in benzene, the sp2 hybrid orbitals will make pi bond, right? And it is unstable because of high angular strain. This bond to be linear, and here it is not linear, so it is in high strain, so unstable. Now further we will add here NS2 negative, so this will attack any of these because both are same here, and then negative charge formed here will take H from here. So finally we'll get our product. So chlorine replaced by NS2, right? If you see its questions, the benzine mechanism, they ask questions of it is a direct substitution or a sign substitution. But in this question, it is not that. It is very simple question. Just simple example of nucleophilic substitution using benzine mechanism, right? So which option we should opt? This one. Sorry. This one, right? Just substitution. Substitution, but how? Elimination followed by addition, right? Yes, everyone? Okay, beta. So I hope this will help you a little bit in quick revision of haloalkanes and haloarenes. Okay, bye.